All right, so now I want us to go to the next stage of information processing in the auditory system. So we talked about how there are these hair cells, we talked about how they have this tonotopic selectivity, and we talked about how when they bend, they trigger these action potentials that get sent down the auditory nerve and into the brain, okay? So what we're gonna focus on now is this movement from the cochlea and primary sensory processing down the auditory nerve and into the brain. And to do this, there's a couple of different synapses that have to be gone through in order to get to auditory cortex itself. So information is going to come down the auditory canal. It's going to go through the cochlea and then up the auditory nerve. That's the very first thing. Then it will go through both the hindbrain and the midbrain and the MGN to get to the auditory cortex. The two things I want to really mention are the hindbrain, midbrain, and I guess also the MGN. So if you remember back in week 3, when we talked about cerebral organization, we talked about the midbrain. One of the things that I said about the midbrain was that it is involved in the orientation of the eyes and body to visual and auditory stimuli. And so this is a kind of instance in which you can see how this is sort of possible. The midbrain is this structure that even before information has gotten to primary auditory cortex is already processing auditory stimuli, such that if you need to kind of divert your attention or attract your attention or something to a sound, your midbrain actually is going to process that information even before it gets to the foreground and allows you to get oriented very quickly. The other thing I wanted to point out in addition to the midbrain was the fact that I referenced here this thing called the medial geniculate nucleus. Okay, this is the thing that hits that goes into the brain right before the auditory cortex. Medial geniculate nucleus hopefully sounds somewhat similar to the lateral geniculate nucleus. So the LGN is the structure that has to, that information goes through in vision. MGN is the structure that information goes through in audition. And what they have in common even beyond that is they're both part of this structure called the thalamus. And if you remember very early on, we talked about the thalamus as this grand central station. And so when information comes in through the sound, through the ears, sound goes to the thalamus in the MGN, that's where this is around here, before it goes to auditory cortex. When information comes in from the eyes, it goes through the LGN. So lateral and medial geniculate nuclei are the same sort of ways that we talk about lateral parts of the brain, medial parts of the brain, and so on and so forth. Okay. Now, a thing though that is definitely different between audition and vision is the way that information in auditory system goes to the two hemispheres, okay? So here I've color-coded these very particularly, okay? So now we're gonna make the left ear, not the left side of like auditory space, but the left ear be color-coded in blue, and we're gonna have the right ear, in this case, color-coded in red. Now, one thing I want you to notice is that in this case, after initial processing, you know, in the brainstem, maybe even up into the midbrain, between this, there's the separation between the red and the blue. Once we get to the cortex, once we get to the MGN and the thalamus, now everything's purple, okay? And the reason for that is that actually both hemispheres, the left hemisphere and the right hemisphere of the auditory system, process information from both the left and the right ear, okay? There is not the separation between the ears, there is not the separation between domains of perceptual space in audition the way that there is in vision. So as a reminder, in vision, there is this separation between the left visual field and the right hemisphere, and then the right visual field and the left hemisphere, okay? So definitely take point to notice that even though there are these similarities that we've been talking about to a certain degree in audition and vision, there's some important differences here between the two eyes, the two ears, the left and right visual field, and the left and right auditory field, okay? Because in audition, again, both hemispheres get input from both sides of space, which is unlike V1, okay? Now, again, just since we're talking about this parallel between V1 and A1, let's just remind ourselves about how the organizing principle of V1 is this thing that we call retinotopy, where if you take something like a monkey and you show this sort of checkerboard spider web type of design on the screen, you can actually see that organizing principle mapped right onto V1. There's this retinotopic map right out there. The organizing principle of A1, as we've talked about a little bit already, is now thought to be referred to as tonotopy, where you can just literally take primary auditory cortex, which is in this part of the brain called Heschel's gyrus, and literally you can just move up and down the cortex as a function of what the frequency is. If you're hearing lower frequencies, this part of the auditory cortex is going to get active. If you're hearing higher frequencies, this part of the cortex is going to get active. So there's nothing about space like there is with V1 with retinotopy. Instead, it's all about tonotopy. And what you really could do, like we talked about in the last time, but just again, as a refresher, is you can see that there are just different neurons and different cells that have different selectivities as a function of the frequency. You can also even see that there's some variation, because here, while A and B are equally specific about different things, here you can see that both C and D seem like they like, similar sounds, but D is actually a little less discriminating than C. D seems like it likes a wider range of things than C are. So when people stick electrodes in primary auditory cortex of monkeys or do this in humans, you can actually see these sorts of selective tuning curves in audition like you can with vision. It's interesting that this one figure is like inverted. Some of you might be wondering, like, why is it an upside down U, whereas usually it's a bell curve like this? I don't know why they did it this way. It's basically the exact same thing. I could have in principle just rotated it 180 degrees, but I didn't. All right, so what are the organizing principles beyond primary auditory cortex, okay? So once you get past this tonotopic map, what are the main dimensions in the brain that are able to process sound? Now, as a reminder, because we've been drawing this nice parallel between vision and audition, what are the organizing principles beyond V1? Well, you've got some regions in the brain that are involved in object recognition. You've got some regions in the brain that are involved in things like faces, bodies, scenes, things like that. We even talked a little bit about size, animacy. So those are the main dimensions of vision beyond V1. But those dimensions don't really make sense beyond A1. Don't really think it makes intuitive sense to have like a body part of the brain or like a body sound part of the brain or a scene sound part of the brain. I mean, I guess you could, but intuitively to me, it just doesn't make as much sense. So the question then is, what is the organization of auditory cortex beyond A1? Usually when I teach this class, and unfortunately when we're not over Zoom, I make people talk to your neighbors about what you think the auditory equivalent of faces, bodies, and scenes are. It's actually really interesting because I always love hearing the types of guesses that people can come up with in groups. There's sometimes some really creative ones, but unfortunately we can't do that now. So instead what we'll do is I'll just tell you the answer, which in this case is the main dimensions that people now know of in audition are pitch, speech, and music. Little typo, that should be capitalized. Or that should not be capitalized. It could go either way. All right, so pitch and the brain. Pitch is a very hard thing to describe in terms of its physical dimensions. It's much easier to kind of understand pitch intuitively if you get a sense of its perceptual dimensions. So what I'm going to do now is play a few clips for you to give you a sense of what sounds that sound like that do and do not have pitch. Okay, so here's one. So that stream of sounds had pitch to it. Now we're going to hear the same streams of sounds with the same frequency, but now it doesn't have pitch. Okay, let's listen to another one. Again, same frequency, but pitch can be turned on and off. It's really complex if you try to explain this physically, so I'm hoping you're at least going to be able to get an intuition there. If someone's whistling, that has pitch. If a toilet's flushing, that does not. If your phone rings, that usually has pitch. If you turn on your shower, that does not. And so it turns out actually that there's a part of the brain that gets uniquely activated when you are hearing sounds that have pitch. And that this is a part of the brain that if it hears whistling, if it hears tones, if it hears music, it will get activated. But if it hears that more like white noise, like type of version of it, it actually won't get activated in the same degree. And so one of the first key areas just beyond primary auditory cortex that you will find in the auditory system isn't going to be for something like objects. Instead, it's going to be for something like it's going to be for something like pitch. Now, it turns out, though, that this pitch area of the brain is not necessarily like the next step after primary auditory cortex. In a kind of interesting way, it actually overlaps with primary auditory cortex. And that's what this, that's what this looks like here. So now what I've done is I've outlined these pitch regions up here in black. And then what I'm showing you here with these sort of like rainbow type things actually is primary auditory cortex. Now, some of you might be thinking to yourself, well, wait a minute, when we were talking about the organizing principle of A1 of primary auditory cortex, we said that it was just like this one straight line from really low frequencies to really high frequencies. It actually turns out that then when you go from A1 to A2, you know, because there's A1, A2, A3, you will actually find that there's this sort of mirror reverse type thing. So A1 will be like this area from blue to red here, and then this area from red to blue there. That's what A2 is, okay? And so what you see is actually that these pitch regions seem to overlap to a certain degree with these different frequencies, which makes sense because pitches can be in different frequency ranges, okay? So now when we want to get beyond pitch in the brain, what I'm going to do is I'm going to take a brain like this, and I've just drawn a few of these little circles. And to give you a sense of it, what the orange and the yellow are up here are those little like rainbows that I showed you a second ago for primary auditory cortex for A1 and A2. So if on this slide I'm showing you, you know, blue, red, blue, I guess I could have made this blue, red, blue as well. So these three little things is that high and low right there. Okay, so now there are these other areas that I want to talk about, specifically these ones that are in green and these ones that are in blue, okay? And this green area is actually a part of the auditory system that's involved in speech, okay? So here is a plot where you're hearing a bunch of different sounds. That's what this legend is down here. English speech, foreign speech, songs, humans, nature, mechanical. And you can see that when it's nature sounds, mechanical sounds, this part of the brain does not get really active at all. But when it's English speech or when it's foreign speech, this part of the brain rather gets really excited. Even when it's music with words, that's what this blue are, you still see that it gets really excited. And so now what's going on down here is it's the exact same data, except it's just averaging over all these clips. So this lighter green bar here is just the average of all the lighter green bars here. This blue bar here is the average of all these blue ones here. The light purple is the average of the light purple, and so on and so forth. And so you can just see that whenever there is a person speaking, be it in music or in one language or another, you can see that this part of the brain is going to get active, okay? Next to it, in this little bluish region here, is a music region of the brain, okay? And so now you can see that the color coding schemes of these plots and of these plots are very, very different from one another, okay? Because over here, whereas green is the two highest between these plots, now you can see that blue is comfortably the highest between these two plots. And again, with music, this is interesting. I don't know why I said again, because I'm saying this for the first time, but you can see that this music region doesn't discriminate between music with vocals or music without vocals. The speech region does, because the speech region really cares about the presence or absence of vocals. Here, the music region doesn't care so much about whether or not it's purely instrumental music or music with vocals. What I'm going to show you now is some actual electrodes from some patients who had some of those electrophysiological implants done in their brain because they have epilepsy. And so here, what you can do is you can actually go into their brain and you can find these individual electrodes that are speech selective. And so what you can see are individual electrodes. So, you know, basically you're finding small clusters of neurons that are going to get really excited by speech selective type signals, English speech, foreign speech, and songs. Songs just means someone singing with words in it. And then down here, now you're seeing the pattern of activity, and we can look at some electrodes that are going to now activate when a person is hearing music. And so this is just giving you a sense of really what the underlying neurophysiology is like, whereas that one before was more of a kind of crude summary. So your brain, as it stands now, the dominant organizing principle for beyond a primary auditory cortex are pitch, speech, music. Pitch, speech, and music are the sort of patches of specificity in the auditory system, sort of like the patches of specificity you get in the visual system for domains like faces, bodies, scenes, and so on and so forth. And one of the most interesting aspects of the specificity of auditory processing actually can be reflected in the specificity of neuropsychological deficits. Now, one of the nice things about talking about deficits in vision is that they're very well understood. We can really see a nice one-to-one relationship between you damage the FFA, you get prosopagnosia. You damage the PPA, you have problems with scene perception. You damage LO, like patient DF, you have problem with object recognition. Unfortunately, in audition, these neuropsychological deficits are much rarer and are way less understood compared to their visual counterparts. So it'd be really nice if I could just kind of walk you through a bunch of different deficits and tell you the exact part of the brain that's damaged. That's usually not the case. Now, there are cases where if you damage the pitch regions or the speech regions, you'll obviously get deficits. But there's some other ones that are pretty poorly understood. So for example, there is a form of agnosia called auditory agnosia. So in this particular case here, if you're listening to a stream of water going by versus a person sneezing versus a car engine, you're going to really struggle to do that, okay? You really struggle to differentiate between what they are. When you hear basic everyday sounds, you have a hard time telling them apart. Interestingly enough, though, a lot of times when people have auditory agnosia, they can still totally understand language. They still have total normal verbal comprehension. They just struggle with processing auditory objects as they were, which suggests that you'd think that you could find some sort of kind of like auditory object regions of the brain, but that actually hasn't really been borne out. So there's this kind of interesting dissociation between neuropsychology and, you know, fMRI and ECOG stuff. There's also a neuropsychological deficit called phonagnosia. This is actually the prosopagnosic equivalent in audition. So if you had to guess, like, what is the equivalent of prosopagnosia? Remember, that's face blindness. You can't tell someone's identity from their face. What do you think that would be in the auditory domain? It's obviously not going to be from looking at a face. It's going to come from identifying them not by their outward appearance in their face, but from the sound of their voice. So you have a deficit if you're a phonagnogic, where you can't identify who someone is, but you can still totally understand what they're saying. You still have total language comprehension and so on and so forth. To give you a sense of what a phonagnosia experiment is like, I'm going to play you some sound clips from some famous people talking. Do me a favor and just see how well you can tell one voice from another. So see if you can understand or recognize these identities.
The man in the red checkered shirt holding his selfie stick.
So that's Morgan Freeman. Here's another one. This one's a little harder.
3. My mom is a film buff, and so I watched a lot of, you know, Rodgers and Hammerstein musicals and films.
That was Scarlett Johansson. Here's a little bit easier one, I think.
There was one concept that I would suggest.
That's Will Smith. I think this one a lot of you can get, hopefully.
Well, me, I'm just an ordinary citizen who believes the...
That's Hillary Clinton. This one I think is by far the hardest. I'm going to play this one twice, actually.
I like, there's actually this, there's this like wellness / yoga / kind of spiritual Netflix called Gaia.
Oh, okay.
And so it's an app you can...
I'll give you a hint. That's a pop singer.
I like, there's actually this, there's this like wellness / yoga / kind of spiritual Netflix called Gaia.
Oh, okay.
And so it's an app you can...
Katy Perry. I wonder if any of you got that it was Katy Perry. All right, so phonagnosia, that's one form of a deficit. Another one we've talked a little bit about is amusia. And amusia actually is one of the rare cases where you could see a nice relationship between the neural organization and the deficit, because if you damage this pitch region that we've been talking about so much, you will become an amusic. So there is a nice one-to-one relationship there. The way you can think about amusia is commonly known as tone deafness. It's an inability to kind of produce or match pitches. Again, if you press 2 keys on a keyboard, I think I've said this before, if you press 2 keys on a keyboard side by side, you know, do, 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 do. A person who has amusia will be like, sorry, I don't know if you're pressing 2 keys or just 1 key again and again. And then my favorite neuropsychological deficit is referred to musical anhedonia. Actually, one of my best friends in the world is getting her PhD at Johns Hopkins. She studies olfaction, and she has musical anhedonia. People who have musical anhedonia derive no pleasure from music, okay? People with musical anhedonia often will say things like, I don't get music. I don't get why everyone is so obsessed with it. I don't get why when it comes on, people get so excited. Like, sure, like, it's nice because there's a rhythm to it, I guess, but they just basically don't get any joy from it. The reason actually that this occurs, it's thought, although it's still kind of speculative, is that there is a lack of a connection in the brain of these people between their music centers and the reward centers of their brain. There's actually this nice connection in most people's brains between reward pleasure centers that produce lots of dopamine and music regions. And with people who have musical anhedonia, if you look at that connection, it's just much, much smaller, or in some cases totally non-existent. My friend actually at Hopkins, Sarah, she's been scanned before, and you can even see with her, like, yeah, that connection's just not there. All right, so hopefully this gives you a sense of what the organizing principles are beyond primary auditory cortex. Again, I just want to reemphasize, I realize that this is a little unsatisfying that you would think that, oh, all these deficits must mean that there are these little modules that correspond to each of all of these different types of things. And that's not just exactly the case. Unfortunately, with Audition, it's not as well understood as Vision. So, I can't necessarily always point to, for example, an auditory object region, although I can point to a pitch region that makes you in music. When we come back after the break, it'll be the last little bit about Audition. We're going to talk about two final things. This will probably be the shortest section of this week. We'll wrap up Audition talking about sound localization and how we can tell where sounds are in the world, because you can tell if the sound's coming to your left and to your right, but we haven't really talked about how your brain does that. And then the last thing we'll talk about actually isn't really about Audition, but I'm going to include it because it involves the inner ear, which is talking about balance and all of the structures in your inner ear that allow you to keep your balance in the world. All right,